Okay, so on to our next video. One thing I want to note here is that I've added onto this equation sheet under work for friction. I now have not only what friction, the friction force and the displacement, but also that the work done by friction is negative the change in the thermal energy that gets produced. And so this is the same thing. With change in thermal energy is negative, the work done by friction. Let me just move the negative over to this side. So I do recommend having an equation sheet sort of like this, or maybe with a couple more even. This is sort of a bare bones equation sheet to have while you're working through some of these problems. I think having them there will help you see, hopefully, the connections between some of these equations. All right, so this is sort of a little different than what we've been doing in our last 3 videos. I want to go back to what we talked about in chapter 7, which is if you have a variable force, it's more complicated to figure out what the work is done by that force on an object during a displacement, because the amount of the force keeps changing, as you're going through. So what value do you use? Well, you have to do the integral, right? If you have a force that's constantly changing as the object is being displaced, you have to pick a force number. Well, you can't pick a force number because the force number is constantly changing. So what you do is you do an integral. And that's what you do when you have something that's changing. That's sort of why there are integrals. That's one sort of reason why there's integrals. And so here you'd actually do the integration. And at number 35 from chapter 7, I'm going to probably wait and see if people have questions about how to do that in class. But you actually would do the integral of a force to get the amount of work that was being done. And again, because forces can vary, this is actually the general definition of work with this integration. But in most of our problems, with some notable exceptions, the force was constant during the displacement. And so this integral just turns into the amount of the force, or the force dotted with Rf minus R naught, or the displacement, which is what that is. So the delta R, which is just our displacement. For conservative forces, so looking back at this work equation here, if you have a conservative force, the work done by the conservative force is the change, the negative change in the potential energy of that force, right? This is what we said about conservative forces. Well, that's the initial potential energy minus the final potential energy. A very complicated way of writing that is this integral. It's the integral of duc from uf to u initial, but it's negative, and so that would give me the initial minus the final. Again, this is uc initial minus uc final is equal to this integral. So I can, for a conservative force, that have potential energies, I can write this top equation where I say the work is equal to this, but that work is equal to negative the change in the potential energy is equal to this integral. So I can replace work with this nasty looking thing. So it's equal to this, where U naught would be when R was equal to R naught. And then UF would be when R was equal to R final. Because of that, I can get rid of the integrals. And I just end up with delta du is equal to F dotted with the R. That can be rearranged to look like this, where I say the force is equal to the derivative of U, the potential energy that goes along with this force. Remember, these are all conservative forces with respect to the position. And dr can be split into a dx part, a dy part, and a dz part, allowing me to get what this would be. So the force would be negative the potential, the derivative, and these are funky looking d's. It means that if u is actually a function of x, y, and z, when you take the derivative with respect to x, you're only taking the partial derivative with respect to that variable x. But this f of x, the x part of our force, would just be the derivative of our u with respect to x. The f sub y would be negative the derivative of the potential energy with respect to y, and the z part, again, would be similarly the negative partial derivative of the u with respect to z. That means if you know your u function, if you know what the potential energy function is as a function of x, y, and z, then you can actually determine the force from the derivatives of that potential. And y'all are going to do number 41 in chapter 8, where you're given u, and it's only a function of x, and so we're only going to end up with an fx part of this. And again, you just do it by doing the derivative. So I can do that here. So my f will be negative the derivative of this thing with respect to x. So the derivative of this with respect to x, I have to do this. I've got an x here and an x here, so I've got to do this separated out. So first I'll just do 4. The derivative of x is 1, and then keep this madness, and then I add, now I'm going to keep the 4x. I'm going to do derivative of e to the x, the negative x squared. So first I just keep e to the negative x squared, and then I multiply by negative 2x, which is the derivative of the exponent. Pulling that all back together again, I end up with, I remember that's the whole thing is negative here. That negative is multiplying the whole thing. So negative 4e to the negative x squared minus, I have 8x squared e to the negative x squared, right? 2 times the 4, I end up with an 8. I have x squared in that, so then I can actually rewrite this. I can maybe pull some stuff out of here. I can have 4e to the x squared. Distribute the negative onto the inside, so I end up with 2x squared minus 1 is what that looks like. I don't have to simplify it, but it looks a little bit less ugly if you do. Again, I multiplied the negative through. This is just a negative 1 at that point. When I pull everything out, this becomes a positive 2x squared, and I pulled out this out in front of it. And so this is the force. And it's all in the I direction. It just requires you to do some integration there. All right. So I need to talk about one last topic in chapter 7 and 8, which is power. So power is another physical quantity. It's typically written as capital P. It's not exclusively capital P. Capital power, or capital P, can also, especially when we start talking about gases, will be pressure. It's probably the more dominant capital P. But we could also just write it out as power. And power is used in a lot of different situations, but in chapter 7 and 8, we're really talking about the rate at which energy is being transferred by a force because of work. So and the rate means how much per time. So rate usually means amount per time is typically the rate, although it sometimes other things. But it is at least a ratio. So amount of energy per time, and because of that, we end up with units of energy per time, which is a joule per second. That's technically a watt, watts, which is a capital W. So this is a capital W that's a unit, watts, not the capital W, which is work. Remember that work actually comes in units of joules, but power, it comes in units of watts, or you could just write it as joules per second. I'm a big joules per second person myself, even when I talk about power. So then there's average power. So average power is that the force delivers or removes energy from our object. And so it's just going to be the amount of work. So this is work here at the top. That the force does, work done by the force over time. Or there can be instantaneous power. So this is the power that the force is providing or removing instantaneously. And this is, not surprisingly, the derivative of the work, or the instantaneous amount of work that's being produced or sent into or out of the object per time. Now, work is itself, right? We know it's this dot product, or we can write it out in terms of amounts. If we do it in terms of the dot product, so if I replace this W with F dot D, I can actually, the force, as long as the force is constant, I can bring the force out of this derivative and keep it over here, and then I end up with the derivative of the displacement with respect to time. Well, the derivative of the displacement with respect to time is just the velocity. It looks a little weird there because you've got a d instead of a dx or a dr, but it's the velocity. And so I can, and this is sort of thinking about it in terms of the actual FD. Again, I'd end up with dd, which is the speed, the cosine of phi. Hopefully the angle is also staying constant. Then we can write it either as the dot product of the force with the velocity. This is our instantaneous power. Or what we already know about dot products, which is the amount of the force, the amount of the velocity, and the angle between the force. So here this would be the angle, as always, angle between our two vectors that we're considering in the dot product. So quickly, we can do a couple of little examples here. These are some of the last problems in Chapter 7, I believe. So we have a block which is pulled at a constant speed. So here's our block, and it's pulled at a constant speed across a horizontal floor by an applied force of 122 newtons directed 37 degrees above the horizontal. So our force is this, where this angle is 37 degrees, and then this block is being pulled basically this way, where our speed stays the same. The velocity, it's being pulled at 5 meters per second. So at what rate does the force do work on the block? This is just P. So P should be our force dotted with V, or the amount of the force times the amount of the velocity times the cosine of the angle between them. So it's 122 newtons, 5 meters per second, the cosine of 37. Sometimes we have really simple problems to finish things off. Cosine of 37, and we end up with 487. And again, this is technically a watt. I may usually write those as joules per second. So this force is delivering 487 joules every single second to this block. Okay, so we need to know the mass. 43 is a little more complicated just because it wants to know the average powers. So compute the work done by the force in the first, second, and third seconds. Those are the average powers. So we want to know the work in the first second over 1 second, right? That's how much time has gone by. So the work done by this force, it's the only force acting on it. We're going to say it's the only force acting on it. And so it's also the work net. So in this case, our work is the net work. And so the easiest way to go about this is do change in kinetic energy for this object. If we have a 5 Newton force and a 15 kilogram body, and our F net is the 5 newtons, that equals MA. So A, and our mass is 15. This is just 1/3 meter per second squared. That's our acceleration. So here my work is going to be the work net, which is the K final after 1 second and compared to the K initial before. Initially, it was at rest for this problem, for this part A. My final kinetic energy is 1/2 mass V final over 1 second. V final is V initial plus AT. I know A, I know my V initial was 0. This is 0.3 times 1 second, and so this is 0.333 meters per second. And so I can use this and say, okay, that's 1/2 the mass times 0.333 meters per second divided by 1 second, and I can get the average power in the first second. 0.5 times 15 is 0.333 squared divided by 1, obviously, is 0.833 joules per second. B, this is for the second. During the second, again, I want the average power, so I want the work over 1 second, but now, again, I could do K final minus K initial over 1 second, but my K initial now is actually using this mass, right? It's using this, so it's the 1/2 mass that velocity, and that's just my 0.833 joules. My final, so I need to know the final velocity. I can still use this equation, but now this is 0.333 plus 0.333 times 2, because that's how many that I'm going into my second. So 0.333, so this is 1 meters per second. So now I'm going to say 1/2 15 1 meter per second minus 0.1/3 meter per second squared, again divided by 1 second. And then we can go through this whole madness. So 1 minus 0.333 squared times 0.5 times 15 is 6.67 joules per second. I would do a similar thing for part C. Now I need to know what is the V final at t equals 3 seconds. Determine what the K final is. The K initial would have been using the 1 meter per second, and I would go through and get P average again. The instantaneous power due to the force at the end of the 3rd second, now that's actually the simpler thing to do. That's the instantaneous, so that's just going to be the amount of the force, which is our 5 newtons, and the velocity after 3 seconds, which is going to be this. So this is going to be the amount of the force, the velocity after 3 seconds, and they're in the same direction. And so the cosine of 0 is how you get that last thing. If we have any questions on that, you're going to ask me in class for number 43. It's just a little bit more, it's kind of going back and using all our kinematic equations, or at least some of our kinematic equations, some of the simpler force issues as well. All right, that's it for chapter 7 and 8. It's a lot of parts. One thing I should say is that lab this week, our lab this week is going to be essentially a big sort of enforced homework set that we'll do all together as a group, or you'll do it as a group, but I'll be roaming around helping to try and work you through a bunch of these types of energy and work problems and give you more familiarity. This is the kind of stuff that's really not that complicated, but you really do have to sort of practice it. And the more familiarity you have it with these types of equations on our equation sheet here, the more they'll all fit together in your brain, and you'll see them all sort of parts of the whole. All right.